Our last talk for the day is going to be presented by Professor Justin Jonas, and it is my very great delight to welcome Professor Jonas to the Winter School. And just to give you a quick bio, so Justin was born in London and immigrated to South Africa with his parents in 1965. He attended the school in Uitenhage, matriculated from Muir College in 1975, and actually enrolled directly in Rhodes University for a BSc degree in 1976. All of his tertiary degrees were obtained from Rhodes University, culminating in his PhD in radio astronomy in 1999. His PhD topic at Rhodes was actually the hard 2.3 gigahertz radio continuum survey of the Milky Way. He has worked in the Department of Physics and Electronics at Rhodes University since 1981, starting first as a research technician and progressing through the researchers and lecturer ranks, and ultimately was appointed as Professor of Physics and Electronics in 2001. From 2003 to 2006, he was seconded to be Managing Director of the Hartebees Radio Astronomy Observatory, or HARTRO as we call it, a post that he held again temporarily as an interim in 2017-2018. He is currently the Chief Technologist of the South African Radio Astronomy Observatory, or SARAO, and is just appointed with Rhodes University. At Rhodes, he is Director of the Center of Radio Astronomy Techniques and Technologies, and that center actually also hosts the SARAO Research Chair held by Professor Oleg Smirnov. He is the recipient of the 2019 Rhodes University Vice Chancellor Distinguished Achievement Award. He has been closely associated actually with the International Square Kilometre Array project since 2001, and was the technical lead for the SKA South Africa team from 2003 until the formation of SARAO. He was responsible for the technical aspects of African proposals to host the SKA, has been intimately involved in the design and construction of the Meerkat radio telescope and its precursors, and he sits on the Science and Engineering Advisory Committee of the SKA proper observatory. His professional interest includes all aspects of observational radio astronomy, from instrumental design through to data processing, and the radio emission from the Milky Way and radio transients and pulsars. Recreational activities include, is a very active man, hiking, road and trail running, mountain biking, dinghy and windsurfing, tinkering in his carpentry and metal workshop, and model boat building. Recently, he has put all his significant skills to work, acting as the technical advisor for the National Ventilator Project. It was an intervention by the South African government to manufacture respiratory support devices to respond to the emergency need that was created during the COVID-19 pandemic. It is our pleasure to welcome Professor Jonas to give this introduction to radio astronomy. Justin, over to you.
Great. So, I'm Justin, and been a radio astronomer in various forms for a long time, and I'm going to attempt to give a real overview of radio astronomy. I know Ruby's already given you an introductory talk, and there'll be some overlap, I suspect, with what I'm going to say, but really is just a very, very general talk about radio astronomy. Now, before you could have radio astronomy, you had to have radio, and so the optical astronomers have been in the business for centuries, because using just eyesight to look at stars, and later on optical telescopes, but really there was no chance of doing radio astronomy until Maxwell had first predicted there would be radio, and radio waves were discovered by Hertz, and of course Marconi later on exploited these radio waves and allowed us to build things like radio telescopes. So just because of this, radio astronomy is a young science. It is just about a century old, actually less than a century old. And I think Ruby's already shown you something like this. Now, that these days modern astronomy extends across the entire electromagnetic spectrum. So on the left-hand side of this image over here, we have the very high frequencies, or very short wavelengths, very high energy photons in the gamma rays. And as you go down in frequency or into longer wavelengths, you go through the X-rays, through the ultraviolet, through the visible, infrared, and then eventually down into the radio, down on the low frequencies. So the radio does cover quite a large fraction of this electromagnetic spectrum. The other thing is that you can only do optical astronomy and radio astronomy directly from the Earth, because the Earth's atmosphere absorbs wavelengths outside of those windows. But then, ironically, we can actually do gamma ray astronomy from the Earth as well, because we actually use the atmosphere as the detector to get Cherenkov light flashes. So when you're down here on Earth, you're limited really to some gamma ray, some optical here in the optical window, and down over here in the radio. And otherwise, you've got to go up into space to use satellites above the Earth's atmosphere. And so that there's this very wide range of different frequencies or wavelengths, photon energies, all equivalent, that we work over. But there is a kind of fundamental difference between what we call radio astronomy down here at the low frequencies, long wavelengths, and the, optical astronomy, or the optical type of astronomy up at the high frequencies. And that is that it's to do with the duality, the quantum mechanical duality of waves and particles. When you're working at very short wavelengths, you tend to have particle detectors. And particle detectors are by their nature incoherent. When you detect a photon, a single photon, you cannot detect the phase of that photon, only its magnitude. Whereas if you're operating in the radio, we have wave detectors. And when you detect a wave, you can detect the amplitude and the phase of that emission. So we call this coherent detectors. So it's a very fundamental difference between the radio astronomy and the rest of astronomy. And the turnover point is around about over here at about 1 terahertz, where you go from dealing with waves to dealing with particles. And really what it is when you're down in the radio regime, rather than in detecting individual photons, because the photons have such low energy, you're detecting billions and billions of these photons. And when they all congregate together, then they actually form a wave. And that's what we detect with our radio receivers. So there is this very fundamental difference between optical and radio astronomy. It means that we can do things, which what this course that you're on is all about, that you can't do in the optical, or certainly very easily. So jumping forward, if you look at the sky, and you look at the radiation that's coming from the sky. Now, we've already said that astronomy these days covers everything from gamma rays down to the radio. And if you start over here and you sort of plot the average power, electromagnetic power that's coming from the sky, if you start on the left over here, which is the short wavelengths, in other words, the very high frequencies, you have a cosmic ray background. And then you come down lower and you start seeing X-rays. And then you come down to lower frequencies or longer wavelengths, and you start seeing optical. And then you start seeing infrared. You see a little peak in the infrared. Then you get this big peak over here. And this big peak is the cosmic microwave background radiation. And this is very high frequency radio radiation. And then down over here, you end up with what's called the cosmic ray background, or basically standard radio astronomy. So you can see that most of the radio signals are quite weak compared to the other electromagnetic radiation that we're getting from the universe, except for the microwave background. So if we go through these things, the cosmic rays are generated by the most powerful, most energetic things in the universe. Explosions and the like cause the cosmic rays. X-rays over here tend to be very hot objects, largely sort of stars and things like that are very, very hot, and they give off lots of X-rays because of the Planck spectrum has a peak in the X-rays. Here, what we have is the stellar objects, the things which are like the stars, like our sun. They kind of peak in the visible, and that's what we're seeing there. Here we're seeing an infrared peak, and that's dust. So there's a lot of dust in the universe. In various galaxies, there's dust between the stars. And so what we're seeing here is things of the order of a few hundred Kelvin. So the stars here are thousands of Kelvin, this is hundreds of Kelvin. Then you get this huge peak over here at the microwave background. And that's basically the Big Bang, the relics of the Big Bang radiation, which is cooled down to 2.7 Kelvin, so very cold over here. And then you end up with radio astronomy down here, which we'll go into later. And Jansky worked for Bell Labs, and this is when radio was just really starting up in the 1930s. And the people who were trying to do early radio transmissions across the Atlantic were bedeviled by this radio noise that they were hearing. And they were wondering where it came from, if they could detect where it was coming from, if they could turn it off so that radio transmissions could happen between Europe and America. And Jansky was given the job of doing this. He built the antenna you see on the left there, which was able to determine the direction of signals. And from that, he deduced that these radio waves were coming from the Milky Way. They weren't coming from the Earth. They weren't coming from the solar system. They were coming from the Milky Way. And Bell Labs sort of basically said, oh, that's tough. We can't do anything about that. And the experiment was stopped. So there's a great irony here that radio astronomy was discovered by radio engineers looking for interference. These days, one of the biggest problems in radio astronomy, as I'll show later, is interference from radios. So, but Jansky was the unknowing father of radio astronomy. The unit of radio flux that we use is called the Jansky, and you can see from the units, 10 to the minus 26 watts per square meter per hertz, that radio astronomy deals with very, very, very weak signals. So Bell Labs put that to bed because they said this is no use to us, and nobody else had the equipment really to do these types of experiments. So nothing happened until the Second World War, when Grote Reber, who was an American engineer, was the first real radio astronomer. He built a radio telescope. He'd read Jansky's papers, and he said, well, let me go looking for these signals. He built this antenna in his mother's backyard, with the intention of mapping these signals from the Milky Way. He recorded his data on chart recorders like this, and you'll see there's sort of underlying waves in those sort of humps in this data, and that's the Milky Way. And then lots of spikes, and all of those spikes that are on there are radio frequency interference, largely caused by motor cars, the spark ignition of motor cars. But he took these charts and using pen and paper, he drew contour maps of the emission that he saw. And so what we have here are sort of simple contour maps of the radio emission that he saw, plotted on galactic longitude and latitude, and you see the Milky Way. You see the radio emission basically mimicked where in the sky the stars were. There was a small embarrassing thing, though, that if you look carefully here, this is galactic longitude as it was determined and defined by our optical colleagues. But the radio data showed that the peak of so it said that the optical people said this is the center of the galaxy at longitude 0. They defined it to be that. But the radio center was about 20 degrees away. They got it wrong. And the reason was dust, that the dust in the galaxy obscured the stars towards the galactic center, and the optical people got it wrong. And the radio people, Reber, as the first radio astronomer, redefined the galactic coordinate system. It wasn't easy to publish this data. It took some years to get it published because the optical astronomers, who were the only astronomers at the time, remember there were no satellites, the only telescopes we had were optical telescopes. They didn't have a mechanism for these radio waves. They didn't believe them. It wasn't a theory about how radio waves could be generated by stars. And so they said this is all rubbish, but eventually there was a half-page paper that was published in Astrophysical Journal. Sort of stepped forward a number of decades. People went about building radio telescopes and mapped the Milky Way in more detail. And this was, in fact, my own data done at Hartfield Hook, showing the Milky Way in the radio. And you can see that I've identified here all sorts of perhaps common things that those of you who know the sky know about. This is the Scorpius region. This is Sagittarius, the center of the galaxy, the small and large Magellanic Clouds, which those of us in the southern hemisphere can see, and Orion, which everybody can see. You can see there's things that happen in the radio. And also other things which we don't see in the sky with our eyes, and we'll come back to this. This is Centaurus A, a radio galaxy, something that radio astronomers spend a lot of time looking at. So that was during the war. Reber built his telescope, And during the war, there were huge advances in radio technology, mostly in the area of radar. And one of the people who was working on radar was Sir Bernard, well, not then, but Sir Bernard Lovell, but later Sir Bernard Lovell, who worked on the H2S airborne radar, quite sophisticated, very sophisticated electronic radar for the era. And when when the war ended, he continued doing innovative things in the radio, and he built the Jodrell Bank Radio Telescope, still one of the largest single-dish radio telescopes in the world, and many discoveries have been made and continue to be made with this telescope. So it was the increase in radio technology during the war that made radio astronomy really viable after the war. So in the 1950s and the 1960s, there was a huge increase in interest in radio astronomy because there was the technology to do it. In South Africa, in the 1960s, there was radio astronomy was being developed here at Rhodes University with some weird and wonderful looking antennas. This one at the top right over here was looking at the sun. These are, you can't really see very well, but these are helical antennas over here. We're looking at Jupiter. And this little dish over here was going to look for water vapor in the galaxy. At the same time, the Hartebeest Hoek telescope was being converted from space use into being a radio telescope. It was built by NASA and was converted into a radio telescope when NASA left. So there was a history of radio astronomy in South Africa going back to the early days. Of course, around the world, things were really picking up, and people were building bigger and bigger dishes. And some of these are, well, all of these are still active today. Then, of course, the late lamented Arecibo dish, which collapsed recently, was up until recently the largest single aperture antenna in the world. And our Chinese colleagues have built FAST. This is during construction of FAST. FAST is now in operation, and a 300-meter telescope, very, very large instrument. But early on in the game, people realized that building bigger and bigger antennas wasn't necessarily the way to go. You could rather build a large number of small antennas to get the aperture that you required. And then there was also the added advantage that you could separate these antennas out. And that allowed you to do aperture synthesis interferometry, which was what your course is all about this week. Martin Ryle was a leader in this at Cambridge, and here's one of our first Nobel Prizes in radio astronomy. So Ryle got a Nobel Prize for inventing, if you like, aperture synthesis interferometry, allowing us to build very large antennas out of lots of small ones. And lots of these interferometers now exist across the world. The VLA at the bottom left there is perhaps the most well-known one out of all. Hopefully not for not much longer, with Meerkat now becoming more and more popular. But the Australians have the ATCA, Indians have GMRT, in the UK have eMerlin, and in the US as well have VLBA. But now the new kid on the block is Meerkat. And Meerkat, with its 64 antennas, is one of the premium radio interferometers in the world, where we do aperture synthesis imaging. And that will, in due course, starting on the 1st of July this year, build out into the square kilometer array, or the mid-frequency aspect of the SKA, and spreads out across a large fraction of the Karoo, building on what Meerkat already has established out there, and Meerkat will become part of this array. And this is all now going to be located on what is now South Africa's latest national park, the Meerkat National Park. And just to show that the SKA is a real thing, this is in fact the first prototype dish for the SKA, which is on the Karoo site. And many more of these antennas are going to be built over the coming years to extend out the SKA. Then, of course, the big daddy of interferometry is very long baseline interferometry, where we link antennas together across the world. So not individual facilities, but you take facilities from around the world and you link them together to do to build up an aperture synthesis array. And you can see that South Africa and perhaps the rest of Africa is very central to these global VLBI arrays, which is one of the reasons that the SKA is located, or will be located in South Africa, that it'll be able to connect up to other telescopes around the world. So what is this radio astronomy thing? For one of the things we do with radio astronomy is we use radio waves as a tool. I won't go through all of this. I think you'll have access to this presentation afterwards if you want to look at the details. But what do? we use these radio waves to study things in the universe. We look at the physics of the emission processes and the local environments of these objects. So we look at individual objects and say, we're getting radio waves from them. How do these radio waves get generated? We can then turn that on its head, and we can say, we detect radio waves, therefore there must be something there. So you can use the radio waves to trace things. You can trace matter distributions and the motion of matter as well. So you're not so much interested in how these radio waves were generated, but what they're coming from and where those things are. You can do physics experiments. You can do very large-scale physics experiments on cosmic scales, which you obviously would not be able to do in the laboratory because of energy and space constraints. So you can test general relativity and all of those sorts of things. And then you can use the radio waves as a tomographic probe. So you'll have something in the background which generates a radio wave. Those radio waves pass through things on the way here. And the way that those radio waves are modified as they pass through those things allow you to study the things that are being passed through. So you can look at the ionosphere, the hot gases and things that these radio waves come through and are effectively disturbed by. And you measure that disturbance and you can see what's in between. So has radio astronomy done anything useful? Well, yep. It's detected what we call non-thermal radiation. We'll come back to this from our galaxy. This is what the optical astronomers didn't believe. They thought there were only thermal sources. Radio astronomy has identified a lot of violent occurrences in the universe, things that are powered by supermassive black holes, very, very energetic occurrences. We've seen that the universe is evolving and the constituents of the universe is evolving. We've seen very cold gas in the universe, which is so cold it doesn't give off any light waves. We see coherent emission, which you don't see at higher frequencies. We see continuum emission from stars and pulsars, detected the cosmic microwave background radiation, come back to that a bit, detected these things called neutron stars, very, very compact objects, which most of them don't give off any light. Got some indirect but very convincing evidence of gravitational radiation. We've detected the evidence of dark matter, detected extrasolar planets, seen gravitational lensing. So a lot of sort of big discoveries have been made. So what are these things that we're looking at? As I said in the previous slide, a lot of the things that we see in the radio come from violent events, from very high, in other words, very high energy events, explosive phenomena, and things that are powered by black holes. It's a lot of the energy source that creates these radio sources is in fact gravity, not nuclear fusion like we have in the middle of stars. It is actually just the potential energy of objects under the gravitational force and gravitational field. So as these objects fall into some gravitational well, they release their energy and comes out in the radio. A lot of the sources we look at are very, very, very distant. We're not blocked by dust or anything, and hence they're also very, very old. And so we're looking back into the history of the universe. And as I said before as well, we can look at very cold things. These cold things, their emission peaks up in the radio. So we see the background radiation, which is basically a black body at 2.7 Kelvin. That's what the universe has cooled down to. And we see the cold interstellar gases that emit spectral lines in the radio, but no other wavelength. So how do these radio waves get generated? So there are two basic generation mechanisms for what we call continuum emission. Continuum emission is very broad band emission. It's not narrow spectral lines, very broad sort of white noise type emission. And the thermal emission comes from when you've got a hot gas, and that hot gas is ionized. So you've got protons or ions which are positively charged. You've got electrons buzzing around because they're hot, they've got a lot of energy. And when they come close to this positive nucleus, they get diverted because of electrostatic attraction. And so you have an accelerated electron. When you accelerate an electron, it gives off a photon. And a lot of those photons are radio photons. It's called free emission or Bremsstrahlung emission. And these are what we call the thermal sources. This works in the optical as well. And then we have the non-thermal sources. And what happens here is you have very, very highly energetic electrons, non-thermal relativistic electrons. These electrons have got high energies, but they're not relativistic. These ones are relativistic. And they get caught up in magnetic field lines. There's a lot of there's a sort of pervasive magnetic field throughout the universe and its constituents. And again, a high-speed electron will get field V cross B forces when it goes through a B field, so it'll circulate around the magnetic field lines. Again, circular motion means acceleration, and that gives off radio photons. So those are our continuum mechanisms. And if you look at the sun with a radio telescope, you see both of these. In fact, you see the disk of the sun. You see the sort of when you look at the radio telescope at the sun, you see a disk, and that's mostly thermal emission from the photosphere of the sun. And then you see these bright spots, and those are in fact our sunspots. So in the optical, they're actually darker. In the radio, they're brighter, and that's caused by non-thermal emission from the sun. If you look towards the Orion region in the sky, here's the Orion Nebula. You can see that with the naked eye, or see it very prettily with binoculars. With a telescope, you see very, very faint emission as well, very faint extended emission, not just stars. And those are nebulae. Those are very hot gas clouds. And if you go and look at that with a radio telescope, you actually see the same thing. So we see what the optical people see. We see the radio nebulae. You can see the Orion Nebula is very, very bright over here. And that's continuum emission. But we also see spectral lines from these sorts of thermal sources. So what you have is very hot gas, it's ionized. And then what happens is an electron which has been knocked off of say a hydrogen atom, there's lots of hydrogen around, will recombine with a proton. And so the electron falls down through all of the quantum levels, all the way down to the ground state. And you know all of this from physics, and you know that the so-called alpha lines are when the electron jumps one state at a time. So it goes from n equals 3 to n equals 2 to 1. But way out here at the very high orbital numbers, it'll jump, say, between 142 and 143, those two quantum levels. And if you look at that energy, between those two energy levels, you work out that you end up giving a radio photon of a very specific frequency. So here you see, when you look at Orion, what you see as a function of frequency, so this is frequency here versus intensity, you see this very, very narrow region, very narrow emission feature, and it's the H92 alpha. That means that the electron has jumped from the 93rd to the 92nd quantum level, and in doing that has given off this very narrow spectral line for hydrogen. Same thing is happening for helium. These lines over here are actually helium lines, and this one over here is a carbon line. So these are very narrow lines. These are spectral lines. We have two basic types of observation. One is for continuum sources. The other one is for spectral line sources. Another very important spectral line is the so-called H1 line, or atomic hydrogen line. The universe is dominated, the baryonic matter in the universe is dominated by hydrogen. About 90% of the baryons are hydrogen. So it's a very useful tracer for things that are happening in the universe, if you can find this hydrogen. Now, a lot of it's tied up in stars, and we see the stars, but a lot of it's not in stars. A lot of it's in gas clouds. Those gas clouds aren't hot enough to radiate in the optical, but they do give off radio emission. And one of the ways they give off radio emission is the so-called spin flip mechanism. So you have hydrogen in its ground state, so it's got a proton here, red, positively charged, here, electron, negatively charged. Both of the proton and the electron have spin, and their spins can be aligned or anti-aligned. And when they're aligned, it's a slightly higher energy state than when they're anti-aligned. So when the hydrogen atom jumps from this state to this state, it loses quite a small amount of energy, 5.87 microelectron volts. And if you turn that into a frequency, it turns out to a frequency of 1420 megahertz, or a wavelength of 21 centimeters. So this is the ubiquitous 21 centimeter line, or 1420 megahertz line, or atomic hydrogen line, or H1 line. All means the same thing, but basically it's hydrogen. H1 is a strange way that astronomers classify atoms. H1 means that it's not ionized. And so it is just atomic hydrogen, not molecular hydrogen, not H2, but just individual atoms of hydrogen. And you can then detect these lines either in absorption or in emission. And again, they're spectral features. They're not wide, they're not broad features. They're very narrow features. So what do we do with astronomy? What do we try to do with astronomy? And basically, I think in a nutshell, one of the things we want to do is we want to understand the entire history of the universe and everything that's in it. So, this is a popular slide that people use for, for introducing this. Over here, we've got the Big Bang at the so-called start of the universe, and over here we have the here and now. Here we are at this stage in the universe. 13.7 billion years have transpired over this time, and the universe started off very hot and dense, and it expanded and cooled. And so there's a lot of sort of theory that goes into this. So if we step through this, we can start over here where astronomy really starts, the so-called cosmic microwave background. Prior to this, this is about 400,000 years after the Big Bang. So remember that's kind of early on in the universe, because the universe is 13.7 billion years. So this is where astronomy starts, because before this, the universe was opaque, and electromagnetic radiation couldn't propagate, so we can't see into that. But here, the hydrogen became neutral and became transparent. And so we can get a snapshot of the universe back over here by looking at the cosmic microwave background. Penzias and Wilson discovered this microwave background, this 2.7 Kelvin radio emission, with this instrument, and again at Bell Labs, same place as Jansky did his work. And again, they were looking for some, sort of pesky interference that was interfering with the early satellite signals. And again, they discovered that it was of natural causes. It wasn't being caused by the instrument and anything else. There was nothing they could do about it. And again, they shared the Nobel Prize for discovering the cosmic microwave background. Later on, people started studying the microwave background in more detail, and in particular, looking at the structure in the microwave background. If you look at the sky, this is sort of looking up at the sky, the microwave background sky, you can see there are red bits which are hot and blue bits which are cold. And these red and blue bits were what formed the seeds for what later became clusters of galaxies and galaxies later on in the life of the universe. This was the COBE satellite which made this picture, and it also showed that the microwave background was an absolutely perfect black body radiator. And that earned, again, Nobel Prizes for George Smoot and John Mather. The latest thing in microwave background studies is the so-called B mode of polarization. It's predicted from theories of cosmic inflation, but it's very, very, very hard to detect, because in order to look at the microwave background, you have to look through the galaxy, and the galaxy presents a very polarized galactic foreground. And so this kind of messes with your data. And if you look up BICEP 2, you see that some people jumped the gun. They said they discovered this thing, but they hadn't, because they were seeing the galaxy instead. So they made a detection, big splash, but then had to retract. So one of the things we're doing here in South Africa is participating in an experiment called CBAS. There's a northern hemisphere aspect and a southern hemisphere aspect. And what we're trying to do is to map the galaxy, the polarization of the galaxy, so that we can distinguish it from the polarization of the microwave background behind. So the CBAS North experiment has mapped the sky. CBAS South experiment is going to be mapping the sky shortly. You can see that you need both north and south to cover the whole sky. And the CBAS North people have analyzed their data, and they show these very, very strongly polarized bits of emission coming out of the galaxy. These big spurs, these big loops and things, and those are related to supernova remnants. So then, moving through the history of the universe, we then go through the dark ages, where the universe had cooled down. Basically, we just had hydrogen and helium, a very smooth universe, no stars, no galaxies, nothing happening. And then, at about 400 million years later, after the Big Bang, the first stars and galaxies start forming. And this is called the epoch of reionization, because what happened there, the stars collapsed and they heated up, and then they reionized the hydrogen around them. And it's expected that what we'll see is the cosmic dawn, the start of stars and galaxies. And if you look at the sky, what the model shows, you'll see these bubbles. These bubbles are being blown by these, being inflated effectively by these first stars and galaxies. So there's a big rush on to detect this radiation from the epoch of reionization or cosmic dawn. It's a big science case for the SKA. And no doubt when somebody discovers this, that will be a Nobel Prize, as yet unclaimed. Again, in South Africa, and participants in this I know are heavily involved in this workshop, We have the Hera radio telescope, radio array. It's a synthesis array out in the Karoo next to Meerkat. You can see Meerkat in the background over here, looking for this radiation from the epoch of reionization. And no doubt you'll hear more about that during this week, particularly from the Cambridge collaborators. Then, after that, you've got the whole sort of evolution of the universe, starting over here with the first stars and galaxies, and then those stars and galaxies and galaxy clusters and all the other constituents of the universe have evolved over time. It's just like, evolution here on Earth of life. If you dig a hole in the ground, the deeper you go down, the further back in time you go, and you see creatures from longer and long ago. Same thing with astronomy. The further you look back, you're looking back in time. You're seeing the things that were there in earlier times rather than what we're seeing now. And so it is like cosmic archaeology that's being done. Of course, the challenge is the further away you look, the things get further away, they get fainter. And you have to build bigger and bigger telescopes to get back, go further in distance and further back in time. So this is why we're building things like the Square Kilometre Array and Meerkat, in fact. So one of the embarrassing sort of dark mysteries, as I call them, in physics and astronomy, is we only actually really understand 4% of the universe. Only 4% of the universe is baryonic matter. 21% or thereabouts is dark matter, and 75% of the energy and mass is this mysterious thing called dark energy. And any progress in understanding these things any further, I'm sure, will also come up to be, come up with a Nobel Prize. And so, not surprisingly, the Square Kilometre Array is a lot of its science case is towards these mysteries in the universe. Okay, so more prosaic. What do we do with Meerkat? What are we going to do with the SK? What do we do in radio astronomy? So I've already said we've got this H1 radiation, this line radiation that comes from the hydrogen. So if you look at an individual galaxy is full of hydrogen, not just in the stars, but in gas clouds. And you can look at that line emission, you can look at the H1 line, and you can map it. You can sort of say, okay, well, that's how much hydrogen I've got. But you could, because it's a spectral line, a very narrow band feature, you can measure its Doppler shift. And because of that, you can measure its velocity, you can measure the velocity of the gas. And so when you look at the galaxy, the color here, this red over here is material moving away from you. The blue is material moving towards you. So you can see that this thing is rotating. So you can measure the rotation of galaxies by looking at the H1 emission. If you look at the centroid of the velocity of this H1 gas, it tells you how fast that galaxy is moving or appears to be moving relative to us. And because of a galactic of cosmic expansion, you can then relate that to the distance through the Hubble constant. So you can learn a lot from by looking at the hydrogen, the H1 emission in the radio from these galaxies. You can look at groups of galaxies, and you can see, so if you look in the optical, there's a galaxy there, and there's a galaxy there. They don't seem to be, there's another one over here, they don't seem to be particularly interested in each other. But when you look in the radio, you can see the cold hydrogen gas that's actually linking these galaxies, and they're pulling each other apart. It's called tidal stripping because of their gravitational attraction. So we can learn more things about the dynamics of these galaxies and their clusters by looking at the hydrogen in the radio. A big topic is active galactic nuclei. So in the middle of galaxies, this is zoomed in right into the middle of a galaxy, mostly elliptical galaxies, there is a supermassive black hole. All galaxies have supermassive black holes in their centers. Some of them are quiescent, not doing anything, and then some of them are active. They're actually doing something, and we call them active galactic nuclei. And when they're doing something, what's happening is that the gravity from this little black hole in the middle over here, I call it little because it's quite small in actual linear size, but of course very massive, material falls towards that black hole because of its gravitational attraction and forms a disk around the black hole, and stuff actually falls onto that disk and it heats that disk up, and all sorts of strange physics happens. This thing gets very, very hot, so you have a bright sort of source in the middle, but through what are still quite mysterious and not very well understood mechanisms, jets of very, very highly energetic material squirt out perpendicular to this disk around the black hole. And these jets squirt out and extend very, very far beyond the galaxy itself. So here's an elliptical galaxy, Centaurus A. So it looks like in the optical, you can see it's got dust clouds in the middle. It's basically an amorphous mass of stars. Doesn't look very exciting. Well, it's quite pretty, but not very exciting. But if you look in the radio, and this is the picture I showed you earlier on in my galactic map, you see enormous emission sort of lobes coming out of this galaxy in the middle here. The galaxy is quite small compared to these. And these jets are squirted out. These are electrons that squirt out, and they spiral around magnetic fields, and they give off synchrotron radiation. So, and these are what we call radio galaxies. So the actual radio galaxy itself extends way beyond the galaxy. And these are very, very interesting objects. Here's some pretty pictures of radio galaxies. They can be classified into two basic categories, the FR1s and 2s, Fanneroff and Riley. Bernie Fanneroff was the founder of SK in South Africa, had a long history in radio, well, had a very early history in radio astronomy in Cambridge, where he classified these objects. But you have the galaxy in the middle, and you have these very well collimated jets squirting out. And some of them have, the FR2s have bright spots on the end of the jets, and the FR1s have bright spots on the inside of the jets over there. So these are these are incredibly strong radio sources. Not all galaxies are radio galaxies. Most radio galaxies are elliptical galaxies. There are one or two spiral galaxies that are radio galaxies, but there are some, as I say, which are just quiescent, and they don't have this. Just to throw this in, this is a very recent picture, press release of a couple of weeks ago, showing a radio galaxy that was imaged by the Meerkat radio telescope superimposed on an optical image. So you can see the optical image of the elliptical galaxy in the middle there, and these beautiful radio jets squirting out. So we look at individual radio galaxies and we try to work out how they work. But if we go back to cosmology, something that I know nothing about, and this diagram here pretty much shows everything I know about cosmology. We know that the universe is expanding. But if we thought that we were in a static universe, if we did a space-time diagram, so this is time on this axis and this is one-dimensional space on this axis, we would just stay in one place in the universe. And light would travel in straight lines. We'd have a light cone. Things are more complicated when you have an expanding universe. We move all of the time. We apparently are moving, everything in the universe is moving away from itself. There's no center of that expansion. But the universe is expanding, and because of that, and the light is basically riding on the fabric of space-time, what happens is that light waves don't just travel in a simple light cone anymore. They actually bend. And one of the aspects of this is that one of the uncomfortable aspects is there are light waves, there are light rays, which will never, ever come to us here and now. They will just carry on diverging away from us, actually traveling away from us. And that's the invisible universe. So there's a visible universe and there's an invisible universe. But the thing that we want to get out of this diagram is that the electromagnetic radiation that is generated early on in the universe also experiences this expansion, and it gets stretched out. So a photon down over here with a certain wavelength ends up with much longer wavelength, so-called redshift. That's one of the important things in cosmology, in experimental cosmology, is we measure this redshift, and through the Hubble constant tells us what's happening how far things are away. So what we do is we can actually use radio galaxies as a tracer of matter. And so rather than trying to study the individual radio galaxies, what we do is we take images of the sky, and all of these dots here are radio galaxies. And looking at the distribution of these radio galaxies, this is an image from Meerkat, the deepest image of the radio sky ever made, can tell us how the universe is evolving. If we do, that's in the radio continuum. If we do that in H1, then because of the spectral lines, we can actually measure the distance to those objects as well. And we can make 3D maps of the universe. And we can see that in the continuum, it looks like things are pretty spread out evenly. That's because we're looking at the universe, the entire universe in one go. If you split it up into different shells of distance, you see that there are these structures that come out, clusters and superclusters of galaxies. So a very big part of radio astronomy. Another thing in the universe is that there are magnets everywhere. Nearly every single astronomical object has a magnetic field attached to it, from the Earth to the Sun, to our galaxy, to intergalactic space. One of the best ways of detecting these electromagnetic, the polarization and the source and the consequence of this polarization is through observing in the radio. Jumping very much closer to home now, when big stars come to the end of their lives, very massive stars come to their lives, they explode as supernovae. And when they do that, they give off radio radiation. So we don't necessarily see stars in the radio, well, they're very faint in the radio during their normal lives. But when they explode at the end, they make these very spectacular radio bubbles. So this is actually sort of a bubble that's being blown by the explosion. Again, Meerkat's been looking at some of these and some truly, truly spectacular images. You can only imagine, what's going on here. You can see a very, very complex structure of these explosions. And it's not just individual stars which that blow bubbles. Our own galaxy, the center of our own galaxy here, is blowing a big bubble as well, detected and discovered by Meerkat. And perhaps something's happening in that's associated with the black hole in the center of our galaxy, which is causing it to blow these bubbles. Our galaxy is not a radio galaxy; it's a eddy creation spiral galaxy. So some really exciting things that we see, and many, many other things in this image. You see all sorts of strange and wonderful things that you would never have seen if it hadn't been for radio astronomy, and for Meerkat in particular. Not really relevant to imaging, but still exciting. Things that we look at in radio astronomy are pulsars detected by Jocelyn Bell, Cambridge, another Nobel Prize. She didn't get the Nobel Prize, but her supervisor did. But basically these very, very, these collapsed stars. So when a big star collapses, it blows off a supernova remnant, but it also then forms a neutron star at its core. This thing here is sort of pretty much the same mass as our own sun, but it's only 10 to 20 kilometers across, and it's spinning. And it has a very, very high magnetic field around it. And the magnetic field, and it's spinning around this axis, but that axis is not aligned with its magnetic axis. And so what happens is you end up with this kind of lighthouse effect through what's called curvature radiation. Radio waves and beams are given off in both directions from the two magnetic poles. And they sweep around the sky. Oops. And if you have a slow pulsar, that's what it will sound like. As it gets faster and faster and faster, you can hear that you're literally hearing the frequency of rotation of these pulsars. So they're very, very interesting objects, quite scary objects. They're very, very accurate clocks, but every now and then the clock goes wrong. And from looking at when the clock goes wrong, we can determine things about what's called the equation of state of the neutron matter that these things are made out of. Again, we can follow these pulses through space, and we can look at this dispersion and the scattering of these pulses to determine what's between us and the pulsars. And most importantly, these things are incredibly accurate clocks. They're very massive, and those are the two things you need to study general relativity. So this will be the ultimate, was Einstein right? And again, this is a big topic for the SKA and for Meerkat. And so testing theories of gravity using black holes and neutron stars and pulsars. It's already through the Hulse-Taylor pulsar, which has shown indirectly that these things give off gravitational waves. There was a Nobel Prize for Hulse and Taylor. Meerkat and other telescopes have shown what's called the Shapiro delay, which is the gravitationally induced delay that's induced into the pulsar signals when they pass by the gravitational field of another object, measured to supreme accuracy by Meerkat. But the biggie is to determine, to measure gravitational waves by looking at the timing changes in pulsar signals. So you have a very accurate clock in the background. Its pulses arrive at very regular times. And if those times are changing in a regular way, it means that space-time is got a bit of a perturbation. It's basically space is moving in between, or expanding and contracting between us and the pulsar. And that'll be a direct measurement of a gravitational wave. So we're doing this with Meerkat. We're doing some incredibly high precision timing of pulsar pulses. So we're using pulsar as a tool, and we're measuring these days now regularly down to 4 nanoseconds for these pulsar times, which is the kind of accuracy and precision you need to detect gravitational waves. The other thing is that pulsars are repeating. They give out a repeating signal. More recently, have been discovered these fast radio bursts, things that just go click in the night once and never come back again, or perhaps come back once every few days. very enigmatic objects, and we need to discover what they are. And of course, is there life in the universe? This is one of the things where radio astronomy really, really does have a big advantage. And I would be surprised if Ruby doesn't speak more about this to you during the week. This is something that she's very involved in. And this is not just detecting SETI, not just detecting extraterrestrial signals, but also just looking for more pragmatic things, prosaic things like the molecules that make up life. But now just to finish off with some real practical stuff. So radio astronomy is hard. It's not an easy subject, or especially if you want to be at the cutting edge. And one of the reasons it's hard is because of interference, radio frequency interference. And this is the so-called L band that Meerkat operates in. And everything you see here, this is frequency from 900 megahertz to 1700 megahertz. Everything you see here is radio interference. These over here are cell phones. This is aircraft radar. This over here is GPS systems. This over here is the galaxy. So this is our own galaxy. It does produce a little signal. Then the rest over here is again GPS and communication satellites. So it's very, you could be very cunning when you do radio astronomy. You have to work in this terrible environment. It's like doing optical astronomy with somebody shining a torch in your eyes. So the first thing you do is you find a place which is intrinsically radio quiet. You go out into the Karoo, where nobody lives, or a very small fraction of people live. The Northern Cape has 4% of the population and 40% of the landmass. And why do you go where there's no people? Because radio waves tend to follow people. Cell phones, radios, radio masts, television signals. So this is a intrinsically radio quiet part of South Africa and of the world. And some of the early work that we did in Soreo, was then SKA South Africa, was to actually go into the Karoo and make measurements of the radio background to see if it was truly quiet. And it was not a good time to be one of my students. Andy Uted in particular had to come out here and spend his time in the Karoo. And then jumping forward to radio telescopes, we built, designed Meerkat. And just to sort of quickly skip through the different components of Meerkat, which is, say, a very recent radio telescope, has been fortunate in that because it's recent, it uses some of the latest technologies and latest thinking in radio astronomy and radio telescopes. So this is an individual Meerkat antenna, so-called Gregorian offset design. You can see it's very asymmetrical. And the reason for doing that is that the path for radio waves coming into the dish is completely unblocked. There's nothing in the way over here. The receiver's tucked away over here. The rays come in, they bounce off this primary reflector, secondary reflector, and into the receiver. And there are good technical reasons for wanting to do that. This is a Cat7 dish, our precursor to Meerkat, which was symmetric and had its receiver stuck in the middle. And because of all this blockage, its beam was terrible. Its so-called primary beam was horrible. And this made imaging difficult, and it also meant that we could pick up satellite RFI across the whole sky. Whereas a Meerkat beam is very much nicer. It's very much more well-contained. And you'll learn in the course that that's a good thing. We had to build all sorts of infrastructure out in the Karoo. This is basically an underground building where we put all the electronics and electrical equipment to stop RFI from escaping. We built the telescopes, though these telescopes are real physical things. There's lots of steel in them. And these were built in South Africa. These are the pedestals for the telescopes. The telescopes are basically reflectors. The reflectors, aluminium reflectors for the telescopes, were built in South Africa. The subreflector is made out of carbon fiber with aluminium sort of infused into it, so that it's also a reflector. All of this needs to be held together with a big steel framework, so-called backup structure. And again, all the welding being done here in Johannesburg, and then put together like a big sort of Meccano set, constructor set on site in the Karoo. And then these dishes get wheeled out, put on a truck. In the meantime, the pedestals have come from Johannesburg, being put down on their foundation, and then you put together a Meerkat antenna. You do that 64 times, and we'll be doing that over and over again for the SKA in the coming future. This is a diagram, I won't go through the details of this either, is basically an overview of the Meerkat architecture, which is the architecture, common architecture really for all radio interferometers. Over here you have a bunch of antennas, 64 in the case of Meerkat. Each antenna has a receiver, and these days we digitize the signal directly. We go from an analog signal to a digitized signal very, very quickly. We ship the data over optical fibers, We go into massive data switches, sort of commercial data switches that are used for commodity networks. We go into what's called the correlator beamformer, which does the initial processing, creates the visibilities that you will be working on this week in the course. And then you go on to the science data processor, again, which is what you're going to be working with in this course. And the data goes onto the archive, that's where you'll get your data from. Very importantly, we have to have very precise clocks and time and frequency references. So looking at the receivers, they're very well-designed receivers. You want to have very sensitive receivers so you can pick up the most faint signals. You can see we pick up both polarizations. There's a dipole. These are two dipoles picking up both orthogonal polarizations. And this whole receiver is cooled down to very low cryogenic temperatures, down around about 20 Kelvin, in order to reduce the noise generated by these receivers. And of course, at those temperatures, you have to have a cryostat. This whole thing is kept in a vacuum to stop the heat getting in and the cold getting out. To say, we take the signal, the analog signal out the receiver, we digitize it immediately, and then we go through a digital signal pipeline over here. And this is the correlator beamformer. Correlator multiplies the signals, the beamformer adds the signals. And then get into the calibration and imaging software, which you'll be working on and make images. The receivers and all the services they require, vacuum services, helium services, the refrigeration for these receivers is helium-based. All other gases would freeze out long before helium liquefies. And so you've got so the vacuum pumps and everything else. The data coming out of this thing is horrendous, and you can't easily process it, so you have to have special purpose processors, these so-called scarab boards based on field programmable gate arrays. So rather than writing a program for a chip, what we do is we program the chip for the special purpose functions that we need for the correlator beamformer. We built these so-called scarab boards, and you put lots and lots of those, hundreds of them together, and this is the correlator beamformer that produces the visibilities that you guys will be working with. And then you go into the science data processor, and this is just a massive, massive compute, a whole lot of GPUs and CPUs in here. And literally, I think, is still probably Africa's largest computer that sits on the back end of Meerkat to process this data. Other people have come along as well, besides ourselves, and stuck their so-called user-supplied equipment onto Meerkat. And so this over here is the Pulsar search engine. So we go searching for pulsars. So again, masses and masses of compute, which search through the Meerkat data looking for pulsars. Another row of computers like this is searching, looking for SETI signals. And these partners come from across the world. The Pulsar people are from the UK, from various parts of the European Union, Australia, and Germany. And so, yeah, that's the quick Cook's tour of the Meerkat telescope. So thank you for your time and attention. Thank you.